Hi friends, in this video we're gonna learn about a brief on MTI radar. So previously we have seen what is a continuous wave radar and what is frequency modulated continuous wave radar. Okay, so in this video we're gonna see what is an MTI radar. Whereas the term MTI indicates moving target indicator. Okay, that means this radar is mainly used to indicate the or detect the moving targets by some principle. Let us look into the block diagram of MTI radar. So before going to the block diagram, the basic definition of MTI radar is MTI radar is a pulsed radar that uses Doppler frequency shift as a means to discriminate moving targets from fixed targets. That means it uses Doppler frequency shift. Previously we have seen what is Doppler effect, right? So suppose my to and fro distance from transmitter to receiver is 2r and wavelength associated be 2r by lambda. Then my phase angle will be 2 pi times 2r by lambda, right? That means it is 4 pi r by lambda. Now my omega will be d phi by dt. That means 4 pi by lambda by dr by dt. Distance by time, it is my radial velocity, right? So it is 4 pi vr by lambda, which is given by 2 pi into 2 vr by lambda, right? So this 2 Vr by lambda is 2 times Fr. So Fr is given by 2 Vr by lambda. This is my Doppler frequency shift, which is given by 2 Vr by lambda. So we are using this Doppler shift to find out the moving targets in MTI radar. Now suppose the only difference between the continuous wave radar and MTI radar is this reference section part, right? There we do not find any reference signal given to the receiver, whereas here we have the reference signal. So from my continuous oscillator, I'll give to power amplifier where it is pulse modulated. My continuous signal is pulse modulated there, and I am radiating into the space with a frequency of Ft, transmitting frequency. So whenever I encounter any moving object, then definitely I'm going to get my Doppler frequency, right? So it is plus or minus my transmitting frequency. So that will be taken to receiver, and in the receiver part, after receiver we have delay line canceller. We'll see what is delay line canceller. Okay, so it delays the output by PRT time units. That means it delays the output by pulse repetition time units and thereby subtracts the original signal with the delayed signal, and we get the information of Doppler frequency from there. Okay, so in this way we get basic Doppler information from delay line canceller, and it is indicated in the indicator. This is how an MTI radar works. Okay, now this MTI radar is of two types. One is coherent MTI, second is non-coherent MTI. So when we do this detecting, what happens is there will be a phase detector here. After it compares the two phases, and the phase difference is given to the delay line canceller. From there we get the delay line information. Okay, now when I draw this amplitude versus time graph for this MTI radar, it will be like this. Okay, so these are the fixed targets, whereas these are moving targets, right? So if there are fixed targets in my when I'm using the radar, then I'll get echoes from the fixed targets, stationary objects. Those are called clutters, which causes error to my receiving signal, right? So I need a filter which can eliminate these stationary clutters, stationary objects, and as my radar important motivation is that to find out the moving targets, not the stationary objects, so I don't need any more these stationary objects, and I use delay line canceller to filter out these stationary objects. How it is done, now we will see. So basically a delay line canceller has a delay unit of PRT time period. From there subtractor to output, right? This is my initial signal, let it be Vi. It is sent to the PRT. Now it is delayed by T time units, and this is my original signal. When I subtract this both, I'll get a signal, or I'll get an output which has FD information. Right? This is a single delay line canceller, whereas there are double delay line canceller also. Right? So how does this eliminate the stationary objects is, now if you can see, moving objects have different amplitudes at different frequencies or at different velocities, right? Now but stationary objects, whatever be the frequency, whatever be the velocity, the amplitude remains constant. So that is the thing which is making easier for the transversal filter or delay line canceller to eliminate them by subtracting. Suppose while subtracting, what happens, subtraction of pulses, as they are fixed echoes are, as these are fixed, even though I delay by 30 time units, they're going to cancel and they are not detected. But when it comes to my moving target amplitudes, these are not constant. Okay, so they are not cancelled and they are detected. Now it is also important for us to know the frequency response of the delay line canceller. It is like, so delay and canceller frequency response is given by this. These are the blind speeds. Okay. This frequency response of the delay and canceller shows that at a frequency 0 and the multiples of FR, the frequency response becomes 0. That means the MTI filters the echoes of the targets moving with the radial velocity due to Doppler shift, which is the integral multiple of PRF. This is the pulse repetition frequency. So the MTI filter, this delay and canceller, filters out the frequencies or filters out the objects which are moving, targets which are moving at a frequency of integral multiple of this pulse repetition frequencies. Okay, so the frequencies whose Doppler frequencies are n equal to FR are eliminated. It has 0 frequencies. Now the speeds or the velocities at which the frequency response of the delay and canceller is becoming 0 is called blind speed. Is called blind speed, right? The velocity at which frequency response of delay and canceller is 0 is called blind speed. It is calculated, it is given by the equation n lambda fr by 2. Okay. Now these blind speeds, what they do is they create range ambiguities. That means for a certain range of values we can detect the range. For certain values we can detect the range, and we can detect even the it is moving target or not. But whereas for certain frequencies or for certain ranges we cannot detect that. This is due to change in the velocity or change in the frequency, change in the wavelength. That is the reason why we go for another method called staggered PRFs. That means now if my delay line, this is my delay line canceller response, right? This is my, let it be for frequency F1. Now if I draw another delay line canceller, this is my for F2, right? So I introduce multiple frequencies at the same time or for delay time, okay, so that if I miss any clutter here, by using first frequency, if I miss it, then using my second frequency I can clear that clutter at the same time, right? So using staggered PRFs or multiple frequencies, this is the main advantage we get, so that to eliminate the clutters completely. Now whenever suppose F2 equal to 2 by 3 times F1, there my 3 times F2 becomes 2F1. There my both the frequencies match, okay. There will be my clutter which is eliminated. This is how this is how staggered PRF is advantageous for MTI radar. Now next comes is two types of radars or MTI radars. They are so here is the two types of MTI radars: coherent MTI radar and non-coherent MTI radar. Once we look into coherent MTI radar, so this has an antenna, duplexer, power amplifier, a mixer, stereo, coho, IF amplifier and phase detector to the delay and canceller, right? Now we'll see how it works. Whenever my coho is given as coherent oscillator, it is the reference supplied to the phase detector along with the mixer. Now this coherent oscillator has the same frequency that of IF receiver, intermediate frequency receiver, right now. So this coherent oscillator frequency is given to the mixer. It is mixed along with the stallo. Stallo is also a stable oscillator. Stallo is stable oscillator, where coho is coherent oscillator. Okay, now these two are mixed and Fc plus Fl is given to the power amplifier, and from there here duplexer also, it acts as transmit receive switch. Okay, at the time of transmitting it won't allow receiver to pass, and at the time of receiving it won't allow transmitter to interrupt, so that it maintains an isolation between transmitter and receiver for power reasons. Now Fc plus Fl, this frequency is given to power amplifier, thereby to the transmitter. So from there it is radiated into the space. Now now duplexer turns as receiver. Now once it receives, as it is a moving target indicator to the given frequency. So we are given, this is the given frequency into a space. When it comes, it adds along with the Doppler frequency of the moving object, right? So it adds along with the moving target's frequency of Doppler frequency. Okay, now from there again it is mixed with FL, the same stallo frequency, which is used both the mixers. This is because here transmitted signal should be in phase with the reference signal in the receiver. That is the reason why we use the same stable oscillator for both the mixers. So here it is subtracted from the FL plus FC plus FD. So I get FC plus FD. Now this frequency is heterodyne to the intermediate frequency. Okay. After that, it is given to the phase detector. It compares it compares the FC and FC plus D, and it subtracts it from that. We get FD. Phase comparison between these two signals, we get the information of FD, and it is given to the delay line canceller. This is how a coherent radar works. So the stallo frequencies would be like IF to RF frequencies for coherent MTI radar. Now instead of this power amplifier, we can also use magnetron oscillator okay, as transmitter. But whenever it is compared with the magnetron oscillator, this coherent MTI radar using power amplifier is much more stable than that of magnetron oscillator. Okay, next comes to non-coherent MTI radar. Non-coherent MTI radar has same duplexer, power amplifier and modulator, pulse modulator, mixer, local oscillator, and IF amplifier and amplifier to delay canceller. Now here it does not use the phase detection, whereas here it is using the phase detection. Here it uses the amplitude fluctuations. Okay, its principle is amplitude fluctuations, right? It compares both the transmitter and receiver amplitudes, and from there it obtains the frequencies, and it is given to the delay line canceller. Here what is the reference signal is clutter. The clutter itself is the reference signal. If there is no clutter, it will not detect the targets, or it will not detect the moving targets. It takes the clutter as a reference signal, and thereby it compares with the moving target signal. If there is no reference signal, there is no detection of moving target indicators. a moving target. This is about coherent non-coherent MTA radars. That's all for this video. Thank you.